Welcome, everyone. Also, those of you who follow us on web streaming. My name is Audun Rossland. I'm the director of the Climate Department in the Norwegian Environment Agency. The fifth assessment report from the IPCC has given the world new and extremely important knowledge. However, the comprehensive report is difficult to communicate in all its details. Still, there is a lot of knowledge in the report that should be better communicated and understood by policymakers. One of the issues we in NEA, and many others I'm sure, wanted to understand better is how the policy choices we make today and in the next 35 years affect the policy options we have in the latter part of this century. Luckily, we knew about people who know a lot about this. Professor Detlef van Vuuren, I hope it's right pronounced, at the Netherlands Environment Assessment Agency and the University of Utrecht has been deeply involved in the IPCC's work on its scenarios. Together with some of his colleagues and the agency, they accepted our invitation to write an assessment on this issue. Today, Professor van Vuuren will present this assessment. Sometime after our seminar, the draft report will be finished and published as a report from the Netherlands Environment Assessment Agency. Professor van Vuuren will speak roughly about 45 minutes, and then we will have a discussion around this topic, which will be led by Kristin Halvorsen as a moderator. We're looking forward to that discussion. So, dear Professor van Vuuren, the floor is yours.
Thank you very much. Let me first of all thank you for the invitation to come over here, and I will enjoy, I think, the discussions a lot about what, our interpretation of the work. So, just to say a little bit who I am and why I'm here. I'm a professor of integrated assessment of global environmental change at the Utrecht University. I'm also a senior advisor at PBL, Netherlands Environmental Assessment Agency. PBL is a part of the Dutch government, but at the same time it's independent by law. So we are supposed to say and criticize as well our ministry. And I was also an IPCC lead author on Working Group 1, Working Group 2, Working Group 3 and the synthesis report. And that's mostly because scenarios play a role in each of these reports, and I'm working pretty much on scenarios. And the reason for this report, as I already explained, was that we had some conversations with the Norwegian delegation already during the acceptance of the report about how to interpret some of the report's findings. And after finishing the IPCC reports, we decided that further explanation would be needed. And one of the things that was very important is clearly the medium targets and how those relate to the degree target. And one of the examples of where I can show you that is in the statement of G7 this summer on the IPCC report, where they said that when they looked at the IPCC report, they wanted to decarbonize the economy, and by 2050 they were considering an emission reduction of 40 to 70%, which they can literally take from the IPCC report. I think many of us don't realize that 40 to 70% is not an expression of uncertainty, but it's mostly an expression of policy choices. And I think that makes a huge difference, because we should not interpret it as 40% is just as good as 70%. By choosing 40% or 70%, we make decisions about what we can do in the long term. And I would like to show that further on. So there are these open questions, and I want to address several of those in my presentation today. And the 5 questions that I will take on, and you will find them as well in the report, is what are current trends leading to, and what would be needed to comply to the international climate policy targets? What are the characteristics of scenarios that are going to 2 degrees? What are the implications for 2050? How feasible are negative emissions? And I will show you in the presentations that negative emissions is an important part of this discussion. And how much flexibility is still present. I will say a lot about model-based scenarios. And I would like to really emphasize that model-based scenarios are not truth machines. They are based on assumptions, on technologies today, and models of how things function, also based on our understanding today. And so, for instance, if a model doesn't have negative emissions, obviously if you use that model, you will not find an outcome that emphasizes negative emissions. That was the situation in AR4. And so many of the results that were published at that time didn't consider negative emissions. Now, in the literature, between AR4 and AR5, many of the models started to add negative emissions. And so you would see that playing a role in many of the scenarios that were published at the time, and as a result, also in the IPCC report. At the same time, maybe we didn't consider as strongly the situation, what would happen if you would not have negative emissions. So that's also not reflected. But there are also other, and I'm just giving this example, but I could have given examples of other technologies that are not in the models and therefore not considered at the moment. And I think that means that if we look at the results, we also have to interpret them in a way that we realize that there are also things outside those models. For instance, lifestyle change is mostly not considered and is something that you can still discuss and see how that will potentially influence the results. So these models are mostly about exploring uncertainty and considering different targets, different pathways to certain goals, and the choices that we might see when we are going there. And the analogy of map making is strongly emphasized by Ottmar Edenhofer, who was the chair of IPCC Working Group 3, and I like it a lot. I think it's a very good analogy. Just somehow exploring different pathways and synergies and trade-offs that you will find. So I had these 5 questions. I will go them one by one. The first question is, what are current trends leading to and what's needed to comply to international climate policy targets? This is actually a graph from the IPCC report, showing you the emission development of the last, from 1970 to 2010. Unfortunately, the IPCC report did not have the emission reduction after that. I will say something about it. A few things to note. One is the majority of the greenhouse gases is from CO2. So the biggest part of the problem, we're simply talking about CO2. That's even more so because CO2 is a long-lived gas. Then, secondly, while we were trying to introduce climate policy from 1992 onwards, we have not been extremely successful in changing a trend. The emissions were going up by about 1.3% globally in the period 1970 up to around 2000. The period 2000-2010 saw very vast emission reductions, increase, and that's mostly driven by fast economic growth in China. The trend continued for a while in the first years of, so 2010, 2013. The last few years we actually saw much slower emission reduction, which is again strongly influenced as well by trends in China, where economic growth has been somewhat slower. So what does that mean for the future? So models try to develop scenarios about the future, and they take into account our expectation of population growth, economic growth, trends in energy use, trends in land use, and this is actually the result of about 400 scenarios published in the literature, and we simply have summarized them in terms of showing the whole range of these scenarios. And you see that almost all of these models expect an increase during the next 50 years, and then probably a further increase, but some scenarios also show some decrease. If you calculate the climate consequences of these scenarios, you would see that the temperature would go up by 3 to 4.5 degrees, which is clearly not in line with our ambition to go to 2 degrees. So how does that compare to the UNFCCC statement of no dangerous anthropogenic interference with the climate system? This is also from the IPCC report. It tries to summarize the potential impacts of climate change. And so here we have the temperature increase compared to pre-industrial, and here we have different possible impacts of climate change, going from impacts on unique ecosystems like coral reefs, which are very sensitive, or mountain systems, from weather events, local risk to agriculture. Here this is global risk, for instance, to agriculture. And then finally, large-scale disruptions of Earth systems, like, for instance, the turnover of the ocean circulation. And they have tried to map those against the global mean temperature increase, trying to indicate whether risks are high or low that these events occur. And yeah, somehow policymakers then need to make a choice. What level of risk is acceptable? To some degree, that choice has been made, because we have already formulated in Cancun that we would like to look at 2 degrees, and maybe consider even strengthening it to 1.5 degrees. Now, if we take 2 degrees as a starting point, we can try to ask ourselves what would be needed to achieve the 2-degree target. And then we have to move from working group 2 of IPCC to working group 1 of IPCC, which made a very interesting graph of how cumulative CO2 emissions over time relate to different levels of temperature. So here we have the cumulative emissions of CO2 from 1870, and we are here now in 2010. 2015 is a little bit further, and this is the future. And here we have the global mean temperature increase according to the models. So this part is historic, this part is calculated by models, and you also see uncertainty. So we simply don't know exactly how much temperature increase will occur. We have a understanding, quite a broad understanding, for the general relationship, but for a specific point, actually, we have uncertainty. And so here we have, if you would emit amount of emissions here on this side of this plume, you're pretty sure that you actually would achieve the target. If you're at this side of the plume, you have the uncertainty, so you could still achieve a 2-degree target, but chances are relatively low. So the reflection here of the plume is the probability, the uncertainty of our understanding of the climate system. So there has been some discussion then how we should translate 2 degrees into targets for CO2 emissions. Do we take a 50% probability, or do we want to take a much lower risk of exceeding the target? Climate scientists can't make that choice. At the same time, policymakers have not expressed what the choice they are making. So at the moment, somehow everybody had agreed that likely 66% is a good interpretation. I don't think there is an official statement somewhere that is should be done in this way, but somehow everybody started to do so. And I think it's a reasonable choice. 50% would be a rather strange interpretation of a target. Maybe we achieve it, maybe not. So we see now that we have taken the 66%, and therefore this would correspond with emitting about 1,000 gigatons of CO2. Now compare this with the already more than 2,000 or around 2,000 gigatons of CO2 that we already emitted. This is quite a low number, and I can show you how low it is on this graph. At the moment, we are emitting around 40 gigatons of CO2, and so this is our baseline again, emitting more than 4,000 gigatons of CO2. Now, let's assume that we want to achieve the 1,000 gigatons of CO2 by going down linearly over time. Then, in about 50 years or so, 50 times, 50 years, yes, sorry, we need to be at 0. Because then you would exactly have emitted 1,000 gigatons of CO2. Now, 50 years is pretty short if we realize that most of our electric power plants have a lifetime of 50 years, or 40 to 50 years. Many of our industrial infrastructure have a lifetime of 40 to 50 years. Many of our housings and urban infrastructure have at least such a lifetime. So if you now build a plant and you want to follow this pathway, and you don't want to decommission them halfway their lifetime, globally, more or less, you have to start building everything without fossil fuel, without CO2 emissions, and to comply to this pathway. So not only in Norway, but also in India, also in China, and also in Africa. And this is quite a challenge, and I think that by itself doesn't seem feasible, certainly if you compare it to what's currently being negotiated. So there are alternatives to achieve it. One is to accept that at some point you start to decommission infrastructure early. We have lifestyle change as an option. But the one option that models really liked in the last 7 years was starting to think of negative emissions. And negative emissions can be achieved. We know that the options are out, and it's not science fiction. And there are at least 2 ways that this might be done. One is by afforestation and reforestation, where you would take CO2 from the atmosphere and put it into the terrestrial ecosystems. The other way that you could do it is by combining bioenergy and CCS. So the growing bioenergy would extract CO2 from the atmosphere, and you would store it underground in CO2 storage. Again, bioenergy power plants are not science fiction. Growing bioenergy is not science fiction. And CCS, as we know, for instance, in Norway from the Sleipner field, is also something that theoretically can be done. So it's an option that we should consider, but it makes our decisions even more complicated to some degree than without, because now all of a sudden in our decisions today, we have to make a decision of whether we believe this technology to be available in 2050 or beyond 2050, and acceptable. And I will come back to that later. So what are the characteristics of scenarios that have a carbon budget of 1,000 gigatons of CO2? I will say a little bit about that. So here we have our baseline. We have here in brown actually an expression of how we as scientists currently appreciate the policy formulations that were on the table. This is actually mostly based on the pledges, so before the INDCs. So this is about the pledges for 2020, and then our interpretation. The INDCs are slightly more ambitious. They're coming down, so that's good news. And then here we have scenarios that are consistent with 2 degrees. These are the scenarios that are consistent with 2 degrees with around a 50% chance of achieving it. These are the scenarios that are consistent with 2 degrees with around 66% chance of achieving the target. And we can characterize them by 4 important phases. One is they need to have somehow a peak around 2020, 2030 in global emissions. Then they have very steep emission reductions in the period afterwards up to 2050 or 2060. Then somewhere around 2060 to 2070, they have to reach carbon neutrality, and many of these have 0 or negative emissions after this. And so these are 4 key characteristics of 2 degree scenarios. If we now further zoom in only on those scenarios that are in this green category, which are around 110 scenarios, I think, in the literature, and they are shown here in green and in blue. And now I've pointed out in green all the scenarios that have negative emissions, and in blue all the scenarios that did not have net negative emissions. They still might have used bioenergy and CCS or afforestation, but it did not result in net negative emissions from 2050 in the second half of the century. And you see that it makes a huge difference. So the blue scenarios need to go down very, very rapidly and then stay at 0. and the green scenarios with negative emissions can be slightly slower. They are still reducing rapidly compared to our business as usual scenarios, but slightly slower, and then they compensate that by negative emissions in the second half of the century. We should not understand this as doing nothing, or for instance like that. I think that's somehow maybe a misunderstanding of what we have been trying to communicate. This is still very ambitious, and more ambitious than the current INDCs, even the green scenarios. So here you see the carbon budget. So we compare now all these pathways compared to the 1,000 gigatons of CO2. And you can see that the blue scenarios nicely try to stay within that, while at the same time the green scenarios go first beyond that, and then using the negative emissions they would come back. In terms of climate system, it's not a big deal. If we have a slight overshoot, the temperature consequences of that are relatively low as a consequence of the inertia that are there anyway in the climate system. But in terms of the risk that you take as policymakers, are we in the end able to achieve these negative emissions? It's obviously a much bigger deal. So this is actually in terms of the energy system an indication of these scenarios. So here we have in blue fossil fuel use without any form of abatement, and then in brown we have all kinds of fossil fuels and bioenergy in combination with CCS, and in green we have nuclear and renewables. And so this is just an example of such a scenario. It's actually the RCP 2.6, which was published a couple of years ago and has been the example of a 2-degree scenario. And so you see that fossil fuels are massively phased out from the system. You also see that so many scenarios, by the way, this would go to zero. That didn't happen in this scenario, partly because it was compensating with the negative emissions and could leave some of the fossil fuels in difficult to decarbonize sectors. So this is actually what's happening if you look at the share of non-CO2 emitting technologies in the energy system. This is the baseline scenario and the whole range in the literature. This is the scenarios consistent with 2 degrees. So by 2050 we need to be at around 60 to 80% of the energy system being dominated by non-CO2 emitting technologies, which is true for the scenarios with negative emissions. So huge decarbonization at a speed that we haven't done before, certainly not in individual countries for such a long time, and then certainly not at the world level. So these are the consequences for individual technologies. And again, I just wanted to point out how different trajectories are for scenarios with negative emissions, the green ones, and without negative emissions, the blue ones. So here we have fossil fuels without CCS, and so in both cases they are phased out, but much more rapidly for the blue scenarios than for the green scenarios. Then fossil fuels with CCS will go into the system. Bioenergy with CCS comes into the system. Bioenergy without CCS may play a role as well in transport, and especially in those scenarios that do not have negative emissions, because then bioenergy becomes a very attractive technology to decarbonize the transport system early. If you have the negative emissions, you can wait a little bit for the electric power technologies to become more competitive. If you don't have that option, you also have to decarbonize transport quite early, and then biofuels might play an important role. Now, renewables are also scaled up much earlier in the scenarios without negative emissions. So one major challenge in the negotiations in Paris is that this doesn't have to happen only in Europe or in the global scale, but something like that needs to happen as well in all regions. So here you have China and India. These are the outcomes of the models. So they're normal development. And if you take EU, you have more or less a straight line in our business as usual scenarios. And then you have to go down rapidly. For China, you actually had projected an increase. And also in this region, somehow around 2020, 2025, you would like to have a peak in emissions going down if you want to achieve the 2-degree target. That's a huge challenge, of course, in the negotiations. So, implications for the 2050 target. And this is a chart that is in the summary of the report, and it's one of the key messages that we wanted to tell. Because in the IPCC report, we had summarized the whole set of scenarios consistent with 2 degrees and saying, okay, in 2050, you would need to have around 40 to 70% emission reductions to be consistent with the 2-degree target. And that's because if you look at the emissions of the greenhouse gases, here measured in total greenhouse gases, Kyoto gases, and we have here all the scenarios that are consistent with the 2-degree target. If you look at the range of the scenarios here, on average, they were reducing emissions by 40 to 70%. In the report now, we try to emphasize this is very different for the green and for the blue scenarios. The green scenarios with negative emissions have an emission reduction for around 40 to 60%. The blue scenarios without negative emissions have an emission reduction of 60 to 70%. Again, these are the scenarios as they are published in the scientific literature. You should be careful not turning it around. So there might be other pathways that have not been considered yet. But in general, you would say, if you don't want negative emissions, you certainly want to be at around 60 to 70% of emission reduction, and not at the 40 range, 40 to 60 range. For OECD countries, these numbers need to be much more ambitious, so 80% or more. But this depends on fairness discussions, and I would leave that out for this discussion at the moment, because that opens another can of worms, which I think is too difficult to handle in one presentation. So how feasible are these negative emissions? So somehow we have now been talking about them quite a bit, but now first of all, we'd like to know why the models liked it, these negative emissions. And what we can see in the models is that with high carbon prices, fossil CCS and bio CCS are very competitive technologies. They simply, based on the cost, they become very competitive. In these models, greenhouse gas CO2 prices easily will go beyond $200 per ton of CO2. And at that point, these technologies are competitive. Renewables are competitive at that price as well, so wind power or PV. But many of those are characterized by the fact that if you introduce more and more into the system, they start to become more and more expensive, given their intermittency and the consequences of that for infrastructure. And so at maybe in the beginning wind power would be competitive with bioenergy CCS. At some point bioenergy CCS becomes simply more competitive. And that's why models choose it. Simply if we don't tell them there are reasons not to choose it, it becomes simply a very attractive. And another point to realize is that bio-CCS, although it has been characterized by some publications in the literature as speculative, I think that's really a wrong word. It's not a speculative technology, it's not science fiction. We can really think of it being created. There are maybe downsides of that technology, but we should consider whether we're going to use it or not. So this is the reason why we might be careful with it. First of all, it depends on storage, and secondly, it depends on bioenergy. And so first of all, for storage, we have some examples of where we try to do storage. And we have successful examples, for instance, in Norway, but we also have very bad examples, for instance, in the Netherlands. So in the Netherlands we did an experiment where we tried to do a storage experiment. The local community really opposed against it, and then we blew it off. We did it a second time in the north of the Netherlands, and again the local community was able to indicate that they didn't want CO2 stored below their houses. So there's first of all, there's a technical question. How much can we store? And we don't know. Here are very different estimates. And some of them are based on oil and gas reserves. And there we are quite sure that if you would store CO2, that it would remain there. But there are also estimates on aquifers where we're much less certain that it's the case. But secondly, there's also this issue of social acceptability of storage, certainly if you do it near urban areas. So if you look at the storage in the scenarios, cumulatively over time, we're talking at least about 2,000, 3,000 gigatons of CO2. So that would be the range here. That's the gray area. And so if we look at the estimates of what is available, this is the IPCC. This is going into the IPCC report, the special report. This is a more recent IEA assessment. So technically it seems that such amount of storage could be there, but we haven't done it. We have simply make an estimate here. And secondly, bioenergy. And we have a similar set of issues there. We can make calculations of how much bioenergy could theoretically be produced, and set sustainability criteria, and for instance calculate what would happen if you don't use forest areas, because if you use forest areas you have high emissions associated with bioenergy. So you can, under a set of sustainability criteria, try to assess how much is available. This is actually from a study that I published myself, but recently the IPCC did it as well, and they said, okay, 100 exajoule by 2050 is most probably available. There's a high agreement that is available. 100 to 300 exajoules is most probably a medium agreement that it's available. Above 300 exajoules it becomes really iffy. But then it is assuming that somehow we're able to organize ourselves globally. And that's still quite difficult, because if we can set criteria for sustainable biomass, but at the same time, if we don't organize the food production, if we don't organize the palm oil production for shampoo at the same time, we all have these problems that if you start producing bioenergy, it might influence the food market, it might influence the palm oil market, and therefore still create emissions. So so there's a lot of opposition also against bioenergy use. So we have a set of technical and social things that we need to consider. It can be done, probably, but do we want to do it? So this is afforestation. This is from the IPCC report. Just wanted to point out that this is cumulative CO2 emissions from land use, and this is positive emissions. These are negative emissions. These are different scenarios. Baseline scenarios mostly have positive emissions due to deforestation, and then we have mitigation scenarios. In blue, the scenarios that are consistent with 2 degrees. Most of them have a negative contribution from land use, but mostly only in the order of around 200 gigatons of CO2, 300 gigatons of CO2. These ones here come from one particular model, which is very optimistic on what can be done. So here we are talking about maybe 1 or 2 gigatons of CO2 per year that we can expect to be stored via afforestation. So BECCS and CCS technologies are not proven yet. The implementation is difficult and controversial, but at the same time it's not like that they're technically speculative. And one of the simply problem for BECCS is maybe bioenergy can be done, maybe storage can be done, but the BECCS itself depends on the availability of those to be present both at the same time. So how much flexibility is still present? Here I would like to say a little bit about how some of these things relate to choices in policy making that we still have to be making. So first of all, how do we deal with CO2 versus other greenhouse gases? And what I'm showing here is the plot that I've shown before from working 1 between the relationship of cumulative CO2 emissions and temperature. But now I show it much more from a working group 3 perspective. And I've here plotted the main relationships between gigatons of CO2 and temperature. And then how it's influenced by either high methane emissions or low methane emissions by the end of the century, and where your temperature would be. And so what you see here is that in principle those methane emissions seem to be relatively small if you compare it by the influence of CO2. But then if you zoom in on a particular target, for instance a 2-degree target, if the methane emissions are very, very high, the budget is only 500 gigatons of CO2. Methane emissions could be on the low side of what models currently show, then the budget might be even around 1500 gigatons of CO2. It is important here to consider whether we are able to reduce methane emissions as strongly. And so most of the models currently say, and these are 2 groups of models that are pessimistic on methane emissions, these are models that are optimistic on methane reduction. But compared to CO2, it's much more restricted. CO2 we go to negative, at least some of our calculations. For methane, it's either 30 to 60%. That's simply because some of the methane emissions come from rice production, from animals, where we simply don't see how we can reduce those to 0 yet. And some of the CO2 methane emissions come from open pit mining, for instance. Now, open pit mining might be phased out simply because of the other considerations for 2-degree scenarios. But at the same time, technologies to reduce those emissions to 0 are also lacking. Another policy choice that we still need to discuss is the 1.5-degree scenario. It's still on the table as a thing that should be considered. And so here we have, again, the relationship between gigatons of CO2, and now I've expressed actually the probability of staying below either 2 degrees or staying below 1.5 degrees. And actually it's the other way around. It's the chance that you overshoot the target. And so so far we have been looking at 66% of staying below 2 degrees, and therefore we take the left side of the blue plume and we end up with 1000 gigatons of CO2. If you would say, no, we want to have a medium chance, I already argued that it would be a bit strange interpretation of the 2-degree target, but then the budget would be around 1500 gigatons of CO2. But if you go to 1.5 degrees, and we can't achieve it with 60, then actually the budget needs to be below 500 gigatons of CO2. Delay makes the story much more difficult. Here I'm showing you some of the scenarios that weighted mitigation until 2020 or 2030. If we would wait until 2030 and then start to reduce, we can't see any option of without massive use of BECCS. So it's really important that somehow the Durban plan is successful and Paris is successful. In this respect, it's still clear from the evaluations of the INDCs that scenarios are not consistent with the 2-degree target yet. So I think personally, assuming that it's not possible to make the targets themselves more ambitious in Paris, it's really, really important that in Paris we get an agreement on being able to make more ambitious targets in the 5 years thereafter. So let's accept everything that's already on the table and then make sure that there is a process to strengthen them. This is my slide that I've showed before, because I think it's the most critical slide in the story that I wanted to tell you about the the 40 to 70%. It's not 40 to 70%. It's actually 40 to 60% if we accept negative emissions. It's 60 to 70% if we do not. And we have a key policy decision here, and somehow we need to make an assessment, and that discussion is still not really done as clearly, openly as maybe we should do. Conclusions. Reaching the 2-degree target is getting increasingly difficult. Scientists have been saying for the last 15 years, you have to start introducing policy now, you have to start introducing policy now. It didn't happen. So there's some skeptical response now to what did you say 15 years ago, you're still saying that it's possible now. People were right 15 years ago. If people would have acted at that time, it would have been much more easy to achieve the target. Still, there is a pathway, but the pathway is getting simply smaller and smaller, and it potentially needs to have these negative emission reductions. Negative emission technology can be a cost-effective component of a mitigation strategy, but it means that short-term reductions targets depends on our assessment of effectiveness of technologies in the long term, which is a complicated thing to do in international negotiation processes. The numbers are 40 to 60% with negative emissions, 60-70% without. And for stringent targets, actually several of the models would not find a solution if CCS is excluded altogether from the set. And that's what I wanted to share to you, and which is mostly in the report.